Okay, so I just want to demonstrate an interesting iteration. Let's take triangle ABC here, okay? And I'm just going to fix A and B without loss of generality. I'm just going to choose some generic ABC here, all right? Now I'm going to also choose a starting point marked here with 0 star, okay? And I'm going to undergo the following iteration. I'm calling this the whirlpool iteration because it looks like a whirlpool. I'm going to start with this chosen point. So the inputs are basically the triangle ABC and this chosen point 0 here. Okay. Now I'm going to go ahead and think of this first triangle here formed by the, whose base is AB and apex at that chosen point 0 star. So you can see this shaded triangle here. And I'm going to compute its centroid. So you can see here that this number 1, or this vertex labeled as 1, is a centroid of the shaded triangle. So I'm going to have my first iteration step departing from 0 for a particular ABC triangle. And I'm going to get, you can see here that if I move C, that doesn't affect the centroid of ABC, sorry, of AB 0 star, right? So I can move C around, and that doesn't affect this point 1, which is the centroid of AB 0 star. Now I'm going to repeat this iteration. I'm going to now consider the triangle. What's the next side of my original triangle? B, C, and that last computed centroid, this number 1 here. And I'm going to compute its centroid. I'm going to go to 2 over here. So 2 is the centroid of B, C, 1. And 1 is the centroid of AB 0 star. So there is a sort of innate iteration going on. I go from 0 to 1, then I go from 1 to the centroid 2 of triangle B, C, 1, the previous centroid, and I'm going to go to the third step, okay, where I'm going to get the last computed centroid over here, 2, and I'm going to form a triangle with the next side of ABC. So CA and the last centroid, and that gives me point 3. Okay, now to get point 4, you do the same thing a fourth time, and now you're computing the centroid, which is this 4 here, of the triangle A, B, and the last computed centroid 3. So is that clear? Now if I now start whirlpooling this around the triangle, I'm just going to continue this on. What we discovered is that this has a limit triangle. This limit triangle here, so if you go from 0 to 1 to 2, 3, 4, 5, 6, and then 7, 8, 9, ad infinitum, okay? You end up getting a limit triangle, and the shape of this limit triangle depends on your inputs. Depends on the triangle, let me be more clear. Depends on ABC, but it does not depend on the choice of the 0 point. So the limit cycle does not depend on the initial point of iteration. Okay, it can be internal, can be here, blah, blah, blah. So you get this sort of terminal triangle. Its centroid coincides with the centroid of ABC, so that's kind of nice. But what was most surprising to us was that the ratio of areas of the original triangle to the terminal triangle is the surprising number 13. Okay, so I'm just going to leave you guys with that, showing a few other examples here. So let me go ahead and move C over there, and you can see that you get a terminal triangle that is independent of the choice of the initial point, but the ratio of areas of ABC divided by the terminal triangle is 13. All right, I'll leave you with that. See you in the next video.